of this library that I'm going to talk about. It's called Verse. Alex Wan is another graduate student, and I'm closely working with John Bullock, who's a student with NIDA. And some of the earlier work was done by Catherine, and I'll mention her specific contributions as well. Okay. So the highlight of this demo is going to be this library that we have built over the last couple of years. It is called Verse. This is a library for modeling and verifying multi-agent systems. So think of them as a number of UAVs with interesting physical dynamics, as well as executing non-trivial software like collision avoidance and detection type of software. And furthermore, they might be operating in interesting environments, like there might be obstacles in the environment, or there might be some geometric constraints about the kinds of paths that the UAVs are allowed to follow. So throwing all of that into a scenario, I mean, describing the scenario itself is a complicated task because the agents are going to be interacting with each other, sharing information, and then making decisions. And on top of that, we are interested in verification, not just simulation. And what I mean by that is if you have some uncertainty in the system, for example, the uncertainty may come from the lack of knowledge about the precise initial conditions of the agents or the precise dynamics of the agents. And maybe even the decision-making process might have some uncertainty, like it can choose to do a left turn or a right turn sometimes. So what verification allows us to do is to explore all of those behaviors that can arise from these uncertainties and evaluate whether the system is behaving correctly or decide whether one of those choices can lead to unsafe or incorrect behavior, right? So that's the verification problem that Verse tries to address. So the internal engine that makes all of this work is hybrid reachability analysis. Today, I will not go into the details of how all this magic works. That could be a whole other talk. But in a nutshell, we are doing this hybrid reachability analysis, which involves both data-driven sensitivity analysis. So for the complicated physics part of the system, we perform sort of this data-driven approach of finding out the sensitivities of the system. It involves computing either Jacobians if we know the white box dynamics of the system, or we get some probabilistic guarantees about the sensitivity. And then for the decision-making part of the system, which is the code that each of these agents are executing, we perform model-based tree search. So this picture here is just showing you a snippet of the kind of tree that is getting constructed inside this verification tool. So you can think of each of these nodes in the tree as a possible combination of states that all the agents might be in. And whenever there is a choice on these decisions, then there will be a fork in this tree. So it's a very flexible framework. It's Python-based. It's fairly easy to get it up and running. There's not a whole lot of dependencies. And we will not be able to discuss all the possible things that you can do with Verse. For example, you can have different kinds of agents, both aerial vehicles, ground vehicles, or even static agents. You can work with different kinds of maps. So a map, simplistically thinking, it defines the environment in which the agent is working. For example, there could be different paths the agent could follow, like these figure eights, or there could be obstacles. And then in verse, we also have a notion of a sensor, which allows us to define what part of the state of one agent is visible to the other agents for making decisions. And there could be even noise in the sensor. So you may not be able to observe exactly the distance to another agent, but some noisy version of that distance. And so we have been developing verse for the last 2+ years now, thanks to the support from the NASA ULI project. And we have been also deploying this tool in a course at Illinois. That has been an interesting experience all by itself. So now every semester, 90+ students in this autonomy course are using verse in their classroom project. So they do some design for autonomous systems. And as a part of their assignment, they are actually using verse to verify their designs and providing sort of high level of assurance or certificate of correctness of their designs. So this is a rather unique thing we have been able to do. I don't think there are too many other tools or libraries that are being used by undergraduate level students in such large numbers for doing this type of hybrid system verification or analysis. Right. So actually, there is going to be a paper in this computer science education conference discussing the impact of verse on educating formal methods to the next generation of computer science and engineering students. So just wanted to mention that. And this is led by former graduate student Catherine Brott. Okay, so that's a snapshot of what we have been able to do with verse so far. Now let me switch gears a little bit and talk about what we are planning to show for this demo in May. Feel free to interrupt and ask questions at any time, okay? So we're thinking of having 2 or 3 parts of this demonstration that we want to make in May. The first one is I would say the biggest chunk. So I'll spend most of my time today to discuss this part. And this is going to be really about demonstrating the core capabilities of verse in performing code level verification for large and complex scenarios for multi-agent systems. And what we are going to do is we are going to have 2 or more agents with realistic aircraft dynamics and running a realistic collision avoidance protocol. And we are going to instantiate this scenario with different types of initial conditions and different types of aircraft, and basically run the verification in real time for the audience to explore the behavior of such scenarios and maybe see when the system is safe, and also discover some corner cases where this particular collision avoidance protocol is not safe for certain types of aircraft and certain initial conditions. Okay, so that's going to be the main plan for the demo. To go into a little bit more detail, we are going to use this Guam model from NASA, which has been transcribed into the JAX framework by Chu Fran's group at MIT. So we are going to use that model for airplanes. And we are going to use the ACAS XU protocol for collision avoidance. And now I'll have more to say about that. So ACAS-XU is a very complicated protocol, and there are different versions of it. There is a neural network representation of the protocol, and we are also working with an approximation of the protocol, which is represented by decision trees. So from our point of view, both are interesting, and they illustrate different ways in which VERSE can handle very complex decision making, either represented by neural networks or complicated if-then-else rules. So in the next few slides, I'll tell you a little bit more about how we are going to demonstrate this, and also some initial results on how far along we are in bringing all of this together. Okay. So the next part of the demo that we are thinking about is verification of flight control systems that use machine learning, and in particular, machine learning for perception, like vision-based control system, like automated landing or formation flight kind of protocols. So we'll spend a little bit of time talking about that today as well, the kind of results we are getting and how the demo might work. And the third possible thing that we are considering, this is still a little bit preliminary and there's some ongoing discussion, is this is Chu Fan's work, is to be able to do post-mortem failure analysis. And the idea here is if you run a complicated experiment and you collect some observation data from this experiment, she has developed some interesting methods which can then do the analysis of this collected data to figure out what were the root causes of problems or degraded performance or failures. This is another thing we can do, because there's going to be a lot of actual flight tests in May. So one potential thing we could do is to collect data from there and do this kind of analysis. Okay, so let me dive in. I'll talk about the first two things, and then hopefully we'll also get some feedback on them and figure out how we could refine these ideas of doing this demo. Okay. Right. So this the Guam plus ACAS scenario would look something like this. On the right here, you have the description of the closed loop system. Let me start from the boxes up here. So this is the physics model of this airplane, which is a model developed at NASA for this lift and cruise aircraft. The aircraft model itself is pretty complicated. It has 26 dimensions, and we will have multiple airplanes. So potentially we could have 2, 3, or even more airplanes in the scenario that we are trying to study. Okay, then the sensor, or this module over here, is going to compute what is the part of the state of one airplane that is visible to the other airplanes for the purposes of collision avoidance. So for this ACAS-XU protocol, the states that matter are the relative pose of the vehicle. So the relative distance as well as the various relative angles. So the sensor is going to compute those relative distances from the states, which is what then goes into the decision protocol. Now we'll look at two different versions of this ACAS-XU protocol. There is the neural network representation of the protocol, as well as a approximation of the protocol that we have created, represented by a decision tree. A little bit more detail about the protocol. So ACAS-XU basically looks at these relative poses of the aircraft and then produces 5 kinds of advisories. Okay. For example, the COC advisory says that the aircraft are clear of collision, so no corrective action is needed. Okay. And similarly, WL, WR are advising the Ego aircraft to make a weak left turn or a weak right turn because there is a potential for loss of separation. And similarly, there is strong left, strong right, right? So those are the 5 advisories that can come out of the protocol. And the neural network version of the protocol actually is represented by 5 or, yeah, depending on how you count 5 or 9 different neural networks, which partition the input space into different layers. So depending on, the relative vertical separation, for example, one particular neural network will get activated, and the output of that would be one of these collision advisories. So that collision advisory then goes out and is fed as an input to the actual aircraft model. Okay, so that's the complete closed loop system. As you can see, so the complexity comes from the fact that there are multiple aircraft involved. Each of them have complex dynamics. The decision-making process itself is pretty complicated. Many different neural networks involved. And if you're working with the decision tree version of the protocol, then again, it's going to be a very large decision tree with like hundreds, if not thousands of branches in that decision tree. Okay, so that's what's running in the closed loop. Okay. And there is this additional complexity coming from the sensors, which are nominally measuring the relative distance between the aircraft, but it could also be more complicated if you want to study, for example, noisy sensors. Okay. Any questions about the scenario or the kinds of scenarios that we are trying to study here? Okay, if there are no questions, let me proceed. Okay, so we have some preliminary results for this type of scenario. We've been able to put together all of this thanks to the work of all the students that I mentioned earlier. And actually other students I left out, like Lin Song did some of the early work doing reachability analysis on the Guam model. So now we can actually and analyze this kind of a scenario using verse. The picture on the left-hand side is a plot of a simulation, or actually a set of simulations from different initial conditions. So the thin blue line is the trajectory of the intruder airplane. And the set of red lines here is showing the different trajectories of the Ego airplane from different initial conditions and following the advisory that came from ACAS-XU. And there's a lot of branching going on here because the different initial conditions might experience different advisories at different times. Okay. And these numbers up here are describing sort of the volume of uncertainty in the system, like what is the range of the initial XY coordinates as well as the various angles of the airplane. Okay, there's not much uncertainty in the position of the intruder. That's why it's sort of like a thin line. And on the right-hand side here is a very similar scenario, but now instead of running a bunch of simulations, we are performing the reachability analysis. So here, the sets that you are seeing cover all the possible behaviors of the system. And again, there is some branching. It's a little bit hard to see here, because the distances are so large. But after the avoidance happens, there is a little bit of branching going on. Yeah, so from these figures, this is very preliminary early results. We've just been able to put everything together. Uh, and these plots are maybe not particularly informative as to understanding whether the scenario was safe or what kind of advisories kicked in. So we're going to work on that and improve the visualization so that when you run a scenario like this or a more complex scenario with multiple airplanes, it would become much more clear, uh, A, whether the scenario was safe or unsafe, but furthermore, to sort of really understand what kind of decisions were being made at what point in time to give the user a very detailed understanding of these types of collision avoidance protocols. Okay. So we have some early thoughts on how this might look. So here's an annotated plot with in 3D. So similar scenario, there's an intruder in blue, and then there's the ego vehicle in red. But this is a plot in three-dimensional space. Again, the left-hand side plot is a simulation. The right-hand side is a reachability analysis. What we have done here is added some annotations manually to give you a sense of what the final visualizations might look like and also to solicit some feedback. So we would annotate these graphs with sort of the advisories that came in, like strong left, clear of collision, etc., uh, to understand like how the system was evolving. And the other thing that we are planning to do is to have a sort of an interactive dashboard to make the uh, demo a little bit more well, interactive so that the users can actually play around with it in real time. So on the right-hand side here, this is a very early mock-up of what the UI for this demo might look like. We are going to improve this, and this is where also some feedback would be great. So we are going to have a part of this UI where the user will be able to drag and drop different types of agents. So you can say, okay, this is going to be a scenario with two agents. One of them is going to have such and such dynamics. Another one is going to have this, Guam type dynamics. And you're also going to be able to set their initial conditions. Okay, so they're 1,000 feet apart or set their altitudes and initial velocities and so forth using this UI. And then you would hit run. And then the verification results are going to appear instantaneously and incrementally. Okay. What I mean by that is generating the full verification result of a scenario like this can take actually quite a bit of time. It can take more than 5 minutes or so in some cases. But that may not work so well for an interactive demo. People will get impatient. So we try to restrict it so that the runs are within 3 minutes. And we are going to make an improvement to the plotting function in the tool so that even before the full computation finishes, the results are going to appear instantaneously, right? So let's say we are trying to do an analysis up to 30 seconds. That takes 3 minutes, but the results will going to start to appear as soon as you hit the run button, so that time will appear to advance slowly, and you're going to see some output right away. Yeah, so that's what we are planning to do for this part of the demo with the Guam and ACAS XU. Any questions or feedback on this part?
I have a question, just in terms of requirements, computing power, and all that, because we need to make sure we have this capability here at Reno. So, do you have an idea what if there's anything special needed?
Great. Yeah, I was going to mention. So we are planning to set this up so that all the computations are going to happen in a server in Illinois. So
Okay,
this visualization is going to be running on a local laptop, or maybe it's also going to be browser based. We are exploring different ways of doing this, Petros, but the backend computation is all going to happen here. So yeah, we don't have to worry about that too much.
okay,
Internet connectivity is definitely going to be required.
sure, sure. Okay,
Yeah, so I have a question as well.
Yeah.
Regarding the decision tree, how do you build it? Like, do you use data to build it?
Yeah, great. Yeah, so I didn't get into that, and in some of the earlier talks, we talked about that in more detail. Yes, so we are sampling the input-output of the neural network,
Mm-hmm.
and we have some choices about the depth and the type of conditions that you can write in the decision tree, what kind of logic you can use in the decision tree, for example, linear inequalities, uh, polynomial inequalities, etc. So once you choose the type of function that you can write in the nodes of the decision tree and how deep you want the decision tree to be, then there are sort of standard algorithms for using the sample data to construct the decision tree. So
Okay.
that's what we have been doing. Yeah.
And have you thought about like building multiple decision trees and running them at the same time to be robust against different situations? Is that a
Uh,
possibility?
yeah, it is a possibility. So yes, yeah, it's a good question. It makes sense to explore uh, decision trees of various sizes and fidelities to see what might be a good enough decision tree representation of this protocol. I don't know if we want to go too far down that road for the purposes of this demo. I think it's an interesting research question. And this
Mhm.
question often comes up actually in one of the earlier presentation was, how do you know the decision tree is a good enough approximation of the actual protocol? And it's a valid thing to try and explore. For the purposes of this demo, maybe that's not the thing that we want to get into.
Mhm.
Instead, we are thinking of the complexity of the decision tree as a way of highlighting the capability of verse in handling complex decision-making processes. Okay, even if it's not like a good representation of ACAS-XU, fine, but it has like look, it has a tree of depth 100 with so many branching conditions, and yet we are able to perform the reachability analysis on it. So give me any protocol, and as long as you can represent it as a if then else kind of a rule, we will be able to do this kind of analysis using verse. So that's sort of the pitch here.
Okay, thank you.
Hi, Sayan. Can I ask?
Yes,
Uh,
please. Yeah.
so, in this intruder ego vehicle states, as particularly to the interactive demo, is the intruder also using GOM dynamics for the demo? Because that might be an overkill, right? It need not be that the intruder, it can be a simple motion model, right?
Yeah, very good. So actually, in these pictures, the intruder is a very simple, like a Dubin aircraft. It does not have the Guam model yet, nor is it running ACAS-XU. This is sort of like the
Okay.
simplest instance of that scenario that you can imagine.
Right.
But what we are wanting to do is to make the scenario more complex and impressive.
Mm-hmm.
And one way to do that is to have both the aircraft have the most complicated dynamics as well as the most complicated decision-making rule. But if you have other ideas of creating such scenarios, very open to that.
Okay. The second question is for the interactive demo. So the feedback for the interactive demo of the vehicle states, is it going to come from the flight real data?
Sorry, what do you mean by that? So the feedback is
The
okay.
vehicle states.
Mhm.
So are you going to use the true experiment data, or this will be again the simulated one?
It's a simulated data, right?
Okay.
So this one is not connected to real hardware
Right.
insofar as the Guam model that has been created by NASA itself represents some real hardware. But
Okay.
all of this analysis is based on that model, which is the
Okay.
typical case for verification, right? You have a model of a system and you have some bounds on the uncertainties, and you're trying to say uh, whether the system is safe or correct.
Okay. The reason I was asking is, suppose if you were to get the true data, I was wondering if you can quantify the model mismatch, with this tool and the simulator what you have with compared to the real data which will be coming from the flight.
So real data during the May demos, or some other source of flights?
Need not be during the demo, but let's say if you were to track the same trajectory with the real flight, and then side by side you have this Guam. Now, the Guam is going to give you a feedback based on the model, but let's say you also have the real data, which is giving different feedback, right? Um, can this tool be used for model mismatch, to quantify?
Yeah. So I understand what you're saying. So that would be like the system identification problem, right? So the Guam model has some parameters, and those parameters were perhaps derived using some actual prototype that NASA has access to. And now we are trying to fit this model for another prototype or some variations in these parameters. Yeah, so that's a valid thing to try and do. The verse verification engine is not, it's not going to provide any special leverage to do that, right? This tool is about give me a model, or it gives you a way of describing very complex scenarios and then analyze whether that scenario is correct or not, or safe or not, right? Whether
Sure.
the model itself is correct, yeah, this is not going to help with that problem.
Okay. Thanks a lot.
Hey, Sayan, this is Kaushik. Just wanted to ask a simple question. You have 5 choices you could make in all of these cases. You're talking about verification results. Is there some way to understand why it made a certain choice?
Yes. Okay. So, um, so for every state where a decision is being made, you can actually go and look at the trace of that execution, meaning you can look at, for every time point in that simulation, what was the state and what was the relative state that went into that protocol, the ACAS protocol, and what was the output. So that would be the finest grain explanation for why a decision was being made at a particular state. Now, that might be too much, right? Because if you look at this, there are like hundreds of simulations going on, and at every point in time along those simulations, some decision is being made. And for a user of this kind of a tool, it might be overwhelming to try and go through all of those decisions. So what we are thinking about is to go from that very fine-grained information where every millisecond some decision is being made to a more abstract view where we'll do some sort of pre-filtering to just illustrate the interesting decisions that were being made. So for example, all this time in the early part of this behavior, if the airplanes are clear of collision, meaning nothing interesting is happening, no danger, right? We will suppress those decisions. And only when something new happens, we will show that to present a more understandable view to the user.
Thank you. That makes sense.
Does that answer your question? Yeah. And will that be useful, or if there is a, we are not experts on air traffic control or these types of things, right? So we are trying to guess what might be useful for people who would ultimately want to use a tool like this to either design protocols or have a deeper understanding of complexity of, scenarios in urban air mobility, whatever, right? We are sort of imagining who the customers of this might be. So if you have any insights about how to present this data that would make that connection more likely, we are very open to changing that.
Yeah, actually, I don't have anyone specific in mind, but we can explore that too, But thanks, Sayan.
Okay, so if there are no further questions on this part, let me move on. And the other two parts are shorter. Okay. Okay, so the next thing that we are thinking about, it's also connected to Verse, but it's different application scenario. Multi-agent is not that important here, but we want to analyze machine learning enabled control systems. This was not a major part of Thrust 2 when the proposal was written 3 years ago, but other parts of this project are using machine learning in a very significant way. So it's sort of natural to also see how to verify autonomous systems that use machine learning. So we are going to look at that. So the kinds of applications we have in mind is vision-based automated landing, vision-based target tracking, and maybe even some exciting scenarios like drone racing, which maybe is not related to urban air mobility, but these are very challenging problems that use machine learning. Okay, so we have actual systems that do vision-based automated landing in simulation, and we are building a system where we do a vision-based target tracking. So for the automated landing, the camera detects some key points, and based on that, it estimates the pose of the airplane relative to the runway, and that pose is then used to compute the control inputs to the airplane. And similarly for pose estimation, so let's say we are designing a controller that is going to follow this airplane that's visible. First step is to estimate the relative pose of the leader aircraft. And then similarly, there is a control pipeline that uses that pose to fly the follower. So we have these systems in simulation, and the ML components mainly come in the form of this pose estimator, either a UNet or a GateNet for estimating the pose of the runway or the pose of the leading aircraft. So the question here becomes, what is the safe operating design domain of the system? This is a term that is used, I think, predominantly in autonomous driving, but it's also relevant for airplanes. It basically defines the range of environmental conditions like lighting, weather, relative speeds, etc., in which the system is expected to work correctly. Okay. So we want to use verification as a way to identify what is the ODD of such vision-based control systems. And we can then sort of visualize the ODD and the reachable sets that are being computed by Verse. either statically or interactively. So here's a quick example of what this might look like. This is for the vision-based automated landing problem. As you see, the view of the landing strip changes dramatically based on the lighting of the environment. So actually, there are two axes to this picture. There are two kinds of variations in lighting: the ambient light along the y-axis and changes in the position of the sun along the x-axis. And as these two lighting conditions change, the pose estimator changes, the behavior of the pose estimator changes, and also the control system behavior changes dramatically. So what we have a technique, again, I'm not going to go into the technique today in detail. There are a couple of different papers describing it, which can identify the range of those lighting conditions under which the vision-based automated landing system works provably correctly. And the range can be computed and generate a heat map like this picture down here. So x-axis is the position of the sun, y-axis is the ambient light, and the green region that has been identified by our technique is the subset of the environment in which, using reachability analysis, we can show that the system lands the plane correctly. Okay. And the reachability analysis itself is being shown in this plot over here. So starting from some large initial uncertain position, the airplane is coming down on the runway. And if you're outside of this green region, it is possible that there will be some simulations of the system that violate the correctness, meaning the plane is not coming down on the runway safely. Okay. So this is the kind of analysis we can do for all of these applications. For the purposes of the demo, we could sort of again use an interactive setup where the user is going to choose the range of the environmental condition that she wants to analyze, and also maybe the range of initial conditions for testing the system. Then the analysis engine will start and generate plots like this. Okay. Now, one of the challenges of this type of thing, both the Guam example that I was talking about earlier, and this type of analysis of vision-based system, is the analysis takes some time, right? Verification typically is not a real-time thing. Software verification runs take 15-20 minutes sometime even longer. People would run these verification things overnight and come back for results the next day because you're exploring a very large state space. So that makes it a little bit challenging to do like a live demo of verification. So again, we have to sort of judiciously choose these scenarios and these uncertainty domains in a way that this verification run can happen relatively quickly. I'm thinking, within like 3-4 minutes, so that some results start to pop up quickly for the users to see them in real time. Okay. Yeah. So that's our plan for the second one. Again, any feedback? Okay. Okay, I see Chuchu is actually online, so maybe...
Yeah, I'm here. Can you hear me?
Yes, so maybe
Great.
you can speak to the last one. Yeah, thanks for joining.
Yes.
Thanks, Chuchu. Thanks. I know you're coming from a seminar. Go ahead.
Yeah, it's a very busy time now, and okay, and I'm sorry
Much
I
appreciated.
joined a little
Much
bit late.
appreciated, right? Thank you. Mhm.
Yeah, my pleasure. So I was discussing with Ryan because a lot of verification thing we were providing is like pre testing, and some of the work we have been doing, which can like help with the verification or testing is post analysis. So we have some ongoing research looking at what we call like root cause analysis for failure cases. Although we all prepare the best and spend all our effort on making this flight test run perfectly, we could expect cases when things do not work well. I have been to quite a few hardware demo at MIT when especially the Lincoln Lab folks were doing those. Although they were very well prepared and not all demo can run at the first time. It took a couple of iterations. So one thing we have been looking at is understanding which factor, especially the hidden factor, could cause the failure of the experiments, especially on the hardware. So here we actually want to hear everyone's feedback on if it's valuable to collaborate with other teams, if they could share their data, like flight data, with the ones that work well and the ones that didn't work. And especially for the one that didn't work, we do not really know what happened to the entire system. So we can perform some what we call post-mortem analysis to understand which factor caused it. We have some preliminary work on an existing data set where they have a 20-dimensional latent space for the flight dynamics. And they run this hardware flight, and they will artificially trigger some failures on the flight dynamics, and you will see like for example, the flight like the pitch angle is not exactly following what is recommended. And then we can do this what we call inverse inference based on Bayesian inverse optimization method to understand which of this factor in the high latent space caused this observed failure, and that can help us perform root cause analysis. So that's something we propose as like a new effort, but it's not really new in the sense like this is not creating new algorithms or running new like machine learning components. It's mostly for collaborating with other teams to see if we can help you perform these root cause analysis for any failure cases you may encounter during your hardware test. So that's in short, but I want to hear people's feedback.
So, Jojo, I have one question. Can you hear me?
Yes. Go ahead. Sorry, I didn't realize I was muted.
Yeah. So, in order to apply the method you developed, so what kind of requirements you need for the system and for the data?
Yeah. So let me just use this flight data as like one example. We need to know the factors that you care about. Okay, like what are the factors, even if it's like not directly observable, but something that we can infer. Like we will need to know what are the interesting causing factors that you care about. And then you can imagine these factors as input go through some black box model. We do not have to have a full information of the mathematics of the model, but output will be the trajectory. And then we will need to grab all the trajectories, including the trajectories that your normal, like your successful trajectories, and then the failure trajectories. And we will use these trajectories and the list of like input that you are interested in to do inverse analysis to tell you what is basically to perform some sort of sensitivity analysis to understand like which factor is most sensitive that could have caused what you have observed.
I see. So based on my understanding, basically you need the data, kind of the trajectory of the system in the normal cases and also in the different failure cases.
Yeah. Yes.
Okay.
So if like I would imagine that if we are going to do some flight test, we will record those data, and those would be basically the data we need.
I see. Okay, one more question. So is this mainly for like a runtime
Oh, it's not
detection or
runtime.
for
It is
post
yeah,
analysis?
it's post-mortem analysis. It's not runtime.
Okay.
Yeah, I think so in this sense, then the coordination will be relatively easy because we do not need any change or modification to the existing hardware architecture to be able to perform this. This is relatively more on data.
I see. Okay, thank you.
Yeah, thanks.
Hi, can I ask a quick question?
Yeah, please.
So this root cause analysis, what would you pinpoint it to? So you're saying that you don't need the flight dynamics to know what the root cause would be?
Yeah, so the couple of things. First of all, if we have the flight dynamics, it will be good because that can make the analysis even easier. What we when we were looking at this problem, we first think like there are dynamics, especially for example, if we want to incorporate the machine learning models, those are difficult to be mathematically described nicely in the module. So and another thing is whatever flight dynamics we have, there will be a gap to the real dynamics. So the method can accommodate to the difference between the simulated dynamics and the actual dynamics. In certain cases, like we have done some analysis on the air traffic management that we really do not have the dynamics, but the method, we basically will learn a surrogate model. So if we do have the dynamics, we probably can ignore the surrogate model learning part, or we can only try to learn that gap, that residual, basically the gap between the model and the actual dynamics, if that helps.
Okay. Could you give me an example of what would this correspond to? Like the failure is because of maybe the ailerons, or is it because the motor didn't operate properly? Like that's
Yes.
what I understand. But what would the root cause analysis give?
Yeah. So we need a list of the possible causes, and we will then that list could, like in this case, it could be the motor failure or some of the structural changes that happened to the airplane. So those would be basically the input. But we do not know what is the which factor actually what happened that could cause what we have observed. In a lot of the cases, is those cause may not be something that we can directly observe.
Right.
Mm-hmm.
Okay. And does this also account external causes? For example, the wind. Especially in these small VTOL aircrafts, the wind can play a significant.
Exactly.
So would it also be able to pinpoint external factors which could cause failure?
Yes, we could. And then it's an interesting question now here because the flight dynamics wouldn't be able to model the wind accurately, and then we can use the data to fill out that gap.
Okay, I see. One last thing is, sometimes these systems, they operate as they're expected to, but still failures can occur. For example, I've been talking to some of the members who have been doing experiments. One possible scenario I can give you is that the VTOL aircraft, it launches from the source, that is from the landing pad, and then it goes into a desired altitude, and then it transitions to a fixed wing. Now, what happens sometimes is, what is happening in the fixed wing mode is that the rotors, the vertical rotors at the front of the aircrafts are rotating to to get into a horizontal position, and the back rotors are going to go off, right? Now, what happens sometimes is that this will cause a dip in the altitude because the aircraft is not fast enough. So naturally, this causes the flight to dip a bit, right? It needs to gain a certain momentum and speed in order to get back to its desired altitude. Now, if we are not careful and if we don't select a appropriate desired altitude, it can cause a crash, right? Now, everything worked as it's supposed to be, but it still caused a failure.
Yeah, I totally agree. I think that would be some interesting like case we could look for collaboration opportunities.
Okay. So those are some uncertain cases which we are not still sure what they could output. Okay, got it. Thanks a lot.
Yeah, thanks. Yeah, I know we are approaching the end of this discussion, but Zaya and I would be happy to discuss and discuss different possibilities here.
Yeah, thank you, Chuchu, for your part of the presentation. And any other comments, feedback on this demo that we are planning to do? Okay.
Yeah, if anything, just feel free to send us an email.
Yeah, sounds good.
Thank you. Thank you. This will be recorded, obviously put on Aviate website and people can watch the recording. Thank you very much for sharing your morning with us. And next time we meet in 4 weeks and we'll listen to the Technical Challenge 3 team on reachability analysis and see how they plan to do their demos. And then 4 weeks after that, we will have Petros and Christos talking more of the physical demos of the vehicles that will be deployed, tested. So as we said, our demo plans are very diverse. We have simulator demos, we have software demos, we have real flight tests, and we'll have some recorded flights from our mocap lab of Illinois, just because we don't want to carry the vehicles and fly there. We'll record good movies and bring. Thank you, everyone. Thank you for your contributions. Enjoy the weekend, okay? Thank you.
Thank you.
Bye.
Bye.
Bye.